So yeah, we were discussing about this is just because we started the recording. We were talking about pipelining, and we saw how pipelining can speed up the overall execution of a set of instructions. It will not increase the. It will not reduce this time it takes for a single instruction to get executed. It's just that overall, if I execute multiple instructions, the overall time it takes to execute multiple instructions reduces. So I have these three instructions and I want to execute it on a unpipelined processor. Each instruction takes 5 cycles. So the unpipelined processor took 15 cycles. And then we decided to divide the 5 stages of the pipeline of the MIPS pipeline as instruction fetch, instruction decode, register fetch, execute, memory, write back. So these are the 5 stages of the pipeline. So I have this timeline, which means that the time moves in this direction. So this is clock cycle 1, clock cycle 2, cycle 3, cycle 4, cycle 5, cycle 6, cycle 7. Okay. So the first instruction 1, in clock cycle 1, I have fetched the first instruction, then I go to instruction decode, register fetch, execute, memory, write back. In the second clock cycle, that's where the pipelining starts to show its magic. In the second clock cycle, when I am doing instruction fetch of instruction 2, when I'm decoding the first instruction, I am doing an instruction decode register fetch of instruction 1. In parallel, I am also doing instruction fetch of instruction 2. So these two are happening in parallel. This is a hardware unit. This is a hardware unit. This is a hardware unit. So these two are running in parallel. In clock cycle 3, when execution unit is acting upon instruction 1, instruction decode register fetch is acting upon instruction 2. The instruction fetch unit is acting upon instruction 3. Right? So this is in parallel. So at the end of 7 cycles, I would have completed the execution of these 3 instructions. So on a pipeline processor with 5 stages, this is taking 7 cycles, whereas an unpipelined processor was taking 15 clock cycles. So this is the idea behind the pipeline. So the other way to look at this is that, let's say I have an so this is a way of me expressing or we expressing in a way of this is a timeline view of what is happening in the pipeline. But you should you should keep it in mind that these things are not getting duplicated, which means that this thing is not a hardware. This is not getting duplicated, right? So this is just a timeline view. But what is actually happening in the system is something like this. So there is an instruction fetch unit. So let's call it as IF. So there's an instruction. So this is the hardware. So I have the instruction fetch. I have an instruction decode, register fetch. That's an hardware. Then I have execute. Then I have execute. Then I have memory. So these are all hardware units. So the instruction 1 in clock cycle 1 goes inside this, which means that the instruction 1 is acted upon by the instruction fetch unit. And then it is moved, whatever it has fetched, it is moved to the instruction decode. So this is in clock cycle 1. In clock cycle 2, I am acting upon this. So this is one instruction. Then I go here, then I go here, and then I go here. So this is the hardware unit. So the instruction 1 passes through this hardware units. So the first unit that it passes is called the instruction fetch. So the instruction fetch is responsible for fetching the first instruction. So it will fetch in clock cycle 1. In clock cycle 1, instruction 1 is fetched by instruction fetch hardware unit, right? So this is the hardware unit that is acting upon it. In clock cycle 2, instruction 1 is decoded and register fetch by the hardware unit called instruction decode register fetch. So this is the hardware unit that is decoding it for you. But at the same time, when this is happening, there is one thing more that is happening in parallel. In clock cycle 2, instruction 2 is fetched by instruction fetch unit. This is the same hardware unit, right? So these two are same. So that is one thing that you have to keep in mind. You are not duplicating the hardware. It's the same hardware that is working on it. So these two, the instruction fetch here and instruction fetch here, are the same hardware unit. So at clock cycle 2, so this is what is happening in clock cycle 2, clock cycle 3, clock cycle 4, and clock cycle 5. At the same time, in clock cycle 2, the instruction fetch is acting upon something. So this is a different way of looking at it. We will not be looking at this way going forward, but it's just for you to understand that we are not duplicating this. There is only one hardware instruction fetch unit. So there's only one hardware. In clock cycle 1, it is fetching instruction 1. In clock cycle 2, it is fetching instruction 2. In clock cycle 3, it's fetching instruction 3. Similarly, an execution unit, in clock cycle 3, it is working on instruction 1. In clock cycle 4, it is working on instruction 2, so on and so forth. So this is just that the way we write it in this is this in this fashion. So we just write the timeline in this fashion. Is it clear till now? Forget about these calls and all those things, but is it clear till now? Okay, I don't know why I have to add question every time. Just give me a second. Okay, I don't know how to add this. Okay. Sorry. Yeah, it will take some time, I think, to come to come up. So, are there any questions regarding this? Do you want to know anything beyond, like, more than what we are discussing? I hope this is clear. The hardware units are not duplicated. Okay, now it should show up. Yeah, so you can answer the poll. If there are no's, then I will try to repeat it. But if it's no, just a second. Yeah, some of you haven't understood. So can I know what you haven't understood? Like, what is the issue? Like, if you just, there is no way for me to add a question there where you can type something. So you'll have to be more expressive. So if you're not understanding, see, this is the basics. If you don't understand, we'll be going a lot into advanced topics. So if you don't understand this, there's no way that you will understand the next classes. So what is that you don't understand? Please tell Aditya, and then he'll tell me, or tell me directly. Yeah, you guys did press no, right, for the poll. So what is that you don't understand? Okay, I will start calling the attendance, and then maybe we'll see. Okay, Dinesh. Gautam. Yeah, is there something you didn't understand?
No, sir.
You understood?
Yes, sir.
Okay. Vaibhav?
Yes, sir.
So is there anything you didn't understand?
No.
Naman Sharma?
Yes, sir.
You understood or not?
Yes, sir.
Okay, Suman? Jaswant?
Yes, sir.
Yeah, understood or not?
Yes, sir.
Gitin George,
Yes, sir. I understood.
Ritika,
Yes, sir. I understood.
okay. Okay. Anyway, I mean that's the best I can do. I think if you guys are not planning to tell me what it is that you don't understand, I can't do anything much about it. Okay. So let's go forward. See, there is definitely okay. Yeah. So we see there are so many people who haven't understood. So I don't know. Should I repeat everything? Aditya, what do you say?
I think, sir, you should continue.
But then why is that like there are people who haven't understood? Like at least they should come out and say, right, this is not done here. I mean, we are putting so much efforts and you guys don't even have the decency to come and tell us what you haven't understood. I'm just asking you. I'm not even. I will not even remember your name, right? So what is that? What are the doubts that you have? I'll stop the class if somebody doesn't speak up. See, in a poll you are saying, anonymous poll you are saying you didn't understand. If I ask you what you didn't understand, you are not telling me. I am ready to repeat any number of times. Okay, I'll also be silent till somebody speaks up.
Sir, please continue.
No. You tell me, like, if somebody has said no, then what should I do, right? There is no point in me continuing if somebody is not understanding. I cannot just teach for a few people in the class. It doesn't work with that way with me. Okay, so we'll meet tomorrow again. Let's see. I'll ask the same question, and if people are able to answer, then we'll go ahead, or else we'll stop the class.
Sir, like, can you say the differences between I-type and R-type instructions once more?
Yeah, that I think no, that will come. I mean, okay, that I will explain. Try to explain again. But did you understand this part of the pipelining? Forget about I-type and R-type instructions. We'll go back to it later again. But is pipelining clear?
Yes, sir.
Sir, you can remove that anonymous thing in the poll so that you know at least.
No, right? Then nobody will answer the poll, right? So see, I am not. See, I don't know. I don't know why you guys think that I'm doing some kind of policing. Okay. Okay. So then we saw that. I hope at least two people who are clear listening to this, it's clear that the unpipelined processor takes 15 cycles and pipeline processor takes 7 cycles. Now I have three instructions. The instructions are a bit different. The first instruction is add R1, R2, R3, subtract R4, R1, R5. You can see that I2 is dependent on I1. So this is what we call as dependent instructions. So here I see that I1 is dependent on I2. Why is it dependent on I2? Because, sorry, I2 is dependent on I1. Why is I2 dependent on I1? Because I1 produces the value R1 and that value is consumed by I2. So there is a dependency of this instruction. So I2 is dependent on I1. So when I run it through the pipeline, so the first instruction finishes execution finishes its entire process in the 5 stages. So in the end of 5 stages, I will get whatever is there of I1. So the I1 would update the contents of R1 in write back stage. We saw that the write back stage updates the content of the registers. In the instruction fetch, I go and fetch the instruction. In instruction decode register fetch, I decode what kind of instruction it is or what instruction it is. I figure out that it is an add instruction. I fetch the contents of R2 and R3 because that's what I have to add upon. In the execute stage, I add R2 plus R3. And then in the memory stage, if it was a memory instruction, I go to the memory and fetch something. In this case, there's nothing. So this will just pass on through this, but I cannot just skip this. We'll see later. And then in the write back stage, I update the contents of the register file. So which means that I would update the value of R1 in the write back stage. So at the end of write back stage of I1, R1 value will be the sum of R2 plus R3. So then when I run instruction 2 through the pipeline, in the clock cycle 2, I will do instruction fetch. In this clock cycle, I cannot do an instruction decode and register fetch. The reason is because if I do a register fetch in this clock cycle, I will get the contents of R1, which is somewhere here, which was produced somewhere here, and not this particular R1. So I cannot do this. So I do a stall here. So there's a stall here. And since this is a stall, since instruction decode for this instruction is not yet done, there will be a stall until here. And only after the end of this write back stage, I will be able to do an instruction decode register fetch again of instruction decode of instruction 2. And then I do an execute memory and write back. So at the end of clock cycle 9, I would have finished instruction 2 execution. I hope at least till now it is clear. So now I will ask you a question and let's see how you guys answer this. So I do an instruction fetch here. So I have fetched the instruction 1. I need to store somewhere. So where will you store that? Like you have fetched the instruction, or let's say I have executed this particular instruction. I have computed the value of R2 plus R3. So where will I store R2 plus R3? So I will write the contents of the register only here. But what do I mean by saying that from clock cycle 3 to clock cycle 4, whatever I have executed, I send it to clock cycle 4. You saw that this is an hardware unit, right? So this is an hardware unit. So it has computed the value of R2 plus R3. Now it has to send it to the next unit. But before sending, it has to store it somewhere before, I mean, it can just not pass it on, right? So there should be something, and that something is called, okay, one question is, how do we know R1 is already in use? Okay, right, okay, so good question. So what somebody is asking is that there was a stall here, and how did I figure out there is a stall here? Because R1 is dependent on this. Now, how did this guy know that I have to do a stall here? Can anybody answer that question? Somebody from your side only has asked this question. So why did I create a stall here? How did it figure out?
Maybe we can have a check whether the instruction that are already fetched are again called like.
No, right? The instruction fetch only fetches the instruction.
Sorry, register fetch.
Yes. So what happens is I actually execute this instruction decode register fetch. When I'm fetching the instruction, I know that there is some kind of dependency because R1 is being used in the previous instruction. So I just stall and I re-execute the instruction decode register fetch. This instruction decode register fetch figures out that, of course, it's not as straightforward as this, but somehow this unit will know that I am fetching something which is not yet produced. So when I'm doing the register fetch of R1, I will know in some way that I am fetching something which has not yet been updated. And what am I fetching? I am fetching R1 because that's what I have to fetch. When I'm fetching R1, when I go to the register file, I figure out that what value I have to fetch is not yet being computed. So I'll be fetching junk value. So that's what is returned here. So that's why it is converted to a stall. And this unit is again executes instruction 2 here. I hope this is clear.
So how are you keeping track of which register is being used?
See, when I do the answer again is not very straightforward, but when I'm doing an instruction decode register fetch here, I know that this is when this is also computing the value of R1. So let's just to make you, just to answer this question, but this is actually a wrong answer, but it's okay if this is one of the design. One of the design decisions that I can do is with respect to every register, I can have a bit. Okay. And when I do an instruction decode register fetch, I will set the bit of R1, which means that it is being used. And I will reset it only after write back. And does this design work for you?
Yes, sir.
Yeah, right. This is just a simple design. Of course, we will build on this. This is a stupid design. This is not the way it is done. But this design works. Why? Because I know that I have set the bit. So when this guy goes and tries to fetch the value of R1, it sees that the bit is set, which means that it cannot now use the value of R1. It figures out that some other instruction in the previous level is being still computing R1. So it will just convert it to a stall and re-execute this at clock cycle 6 when that bit is set. Okay, so let's assume that is possible. But the other important thing is that when I fetch an instruction when I fetch an instruction, after fetching an instruction, I am storing it in a register here. When I do decode an instruction, the output of this particular unit is stored in a register here again. When I execute, I am storing it in a register here. In memory, I am storing it in a register here. So whatever I fetch from memory, this unit has fetched from memory. So I am storing it in a particular register, and that register is called memory write back register because it is the register between these two. There is no need for me to have a register here because write back would complete and the instruction would complete here. So there are 4 registers where they store intermediate values of the pipeline execution units. So what are the pipeline execution units? It's instruction fetch, instruction decode, register fetch, execute, memory, and write back. So this particular register here, after the instruction fetch hardware unit fetches the instruction, before it can pass on, because it can pass on to this instruction decode register fetch only in clock cycle 2. Only in clock cycle 2, whatever I have fetched can be passed on to the next execution unit. But I have fetched it in clock cycle 1, so I store it in this register. Right? I store whatever I have fetched. Like let's say, let's say I have fetched. Let's say I have fetched instruction 1. At the end of clock cycle 1, this register will have whatever is here. It will have instruction 1 here. Okay. And in clock cycle 2, it will have the decoded value of I1. Whereas in clock cycle 2, this would be erased. This would be erased. And what will be here in clock cycle 2? At the end of clock cycle 2, what will be here?
I2.
It will be I2, right? So that's all. So you are storing whatever you have done in that clock cycle. In clock cycle 1, this register, particular register, at the end of it will have I1. In clock cycle 2, this guy will go and say, hey, whatever you stored here, and it will go and fetch that and act upon it and store it here. So that is how the hardware works. So in clock cycle 1, I go and fetch the instruction 1 and it will store it here. In clock cycle 2, this guy will say, oh, what have you fetched? And go and get this register value here. And that is I1 here. And it will act upon it. It will decode the instruction and store it here in clock cycle 2. Whereas in clock cycle 2, anyway, this would have been moved away. So now I will go and fetch the I1 here. If it is not clear, it will get clear in a moment. So we'll go back to this particular instruction set, instruction stream. What was that? It is add. Yeah, can anybody remember and tell me what was it? It is add R1, R2, R3 and subtract
R4, R1, R5.
Okay, R4, R4, R5. Thanks. Okay, so now let's pull up the pipeline, right? So I have clock cycle 1. This is instruction 1. I have instruction fetch, instruction decode, register fetch. Clock cycle 3 execute, clock cycle 4 memory, and in clock cycle 5 execute. Sorry, write back. So this should come in your dream. If somebody says in your dream instruction fetch, you should say instruction decode, register fetch, execute, memory, write back. Right? So at the moment, every time you're using your mobile, it is always saying fetch, decode, execute, memory, write back. It is saying again and again. That's why you're able to see all your YouTube videos. You're able to play a game, everything, right? So it's always saying that. So you should also keep saying that. Anyway, so this instruction 1 did this. Now I have instruction 2. I did an instruction fetch. Right? Now there is this instruction decode, register fetch, but there is a stall here. Why? Because I cannot fetch because the R1 value is completed here. So there's a stall here, there's a stall here. And then there is instruction decode, register fetch again, and it continues. Now my question is, what was I3? I3 was add R7, R8, R9, right? I3 was add R7, R8, R9. Okay. So can I do an instruction fetch? Here is my question.
No, sir. Otherwise, I2 will be removed.
Yes, so that is very important. So this is one of the takeaways for today's class, because we didn't cover too much. I cannot do an instruction fetch here because the moment you can see, if you see this view, you think that I can do instruction fetch. Why? Because anyway, you see that, okay, I2 instruction fetch of I2 is done. So why can't I do instruction fetch of I3? That's easier to think, right? Because you have finished instruction fetch of I2. Now, why can't I do this, right? Why can't I do this? You will think that, okay, since instruction fetch of I2 is done, I will do instruction fetch of I3, but I can't do this because of the view I am doing here. If you see the view here, what has happened in clock cycle 2 is this instruction fetch of I2 is it's still continuing to be here. Why? Because I cannot do an instruction decode register fetch of I2 in the clock cycle 3, right? I cannot do, sorry, in clock cycle 3, I cannot do instruction decode register fetch of clock cycle 3 here. So I am waiting for this guy to pick this up. And when will this guy pick up this particular instruction? He will pick up only in clock cycle 6. Is this clear?
Yes, sir.
Yeah, I cannot do an instruction fetch here. The reason is because I have fetched I2 here, and this hardware unit will pick up this I2 only after clock cycle 6, right? You can think about it in another way. You can think that there is a pipeline register here, right? So it's the same register that is here, right? So I have now this register is storing whatever it is storing, right? It is storing this register is storing I2 here. Now, if I go and fetch I3, if I go and fetch I3, what will happen is this will be overwriting whatever is there in I2, and you will lose that, right? So I cannot do this. So in a pipeline, irrespective of what kind of pipeline you are building, if there is a stall, that stall percolates till the end. So in that clock cycle, you cannot do anything for any instruction. So if I figure out that there's a stall, that stall percolates till the end. So I cannot do anything. So this clock cycle 3, once there's a stall, it's a stall forever. So this clock cycle 3 will not be able to do anything. This is very important for you to understand. Once there is a stall, I cannot do an instruction fetch. So when can I do an instruction fetch? I will be able to do an instruction fetch only here, when this guy picks up this particular instruction fetch. Is this okay?
So you said that the stall percolates down, right? So maybe if by any chance we are not performing the instruction fetch operation there, but maybe somehow we are like doing some other operation that can be done or not.
No, it cannot be done because you will be messing up with the register. So these are the 4 registers that you should know about. These are the 4 registers. These are called pipeline latches. If you read a textbook, it will be called as pipeline latch. Latch is nothing but a register. So there are 4 pipeline latches, 4 registers in this pipeline. So the first pipeline latch or register is this instruction fetch, instruction decode latch, and the other is instruction decode execute. The other is execute memory. They are named by what they are combining together. And this is called memory and write back latch. So there is an instruction fetch, instruction decode latch. There is an instruction decode execute latch. There is an execute memory latch, and there is a memory write back latch.
So these are independent of the 0 to 31 numbered registers.
Yeah, these are completely, these are not the registers that the register file is talking about. These are the registers which are pipeline registers. In the pipeline, this is a hardware unit. There are 5 hardware units, right? So each hardware unit will have a register which will store at the end of the clock cycle what it has done. You had given it a task. What is the task of this particular hardware unit? The task of this particular hardware unit is to fetch an instruction. So in that particular clock cycle, it will fetch an instruction, and at the end of the clock cycle, it will keep it in its register. In the next clock cycle, the goal of this particular hardware unit is to go and fetch whatever is there in this register. Whatever is there in this register, it will go and fetch, decode, and keep whatever it has decoded in this register. In the one more clock cycle, what is the goal of this execution unit? The goal of this execution unit is to fetch whatever is written here, execute it, whatever that execution means to it, and keep the values in this register. And similarly, whatever is this is, we'll go and fetch here, and if it has to do something, it will act upon it. If it's a load instruction, it would have got an effective address. It will go to the memory, fetch the contents, and keep that in the register. Finally, the write back will pull out from this register and update the content of the register file.
Sir, there is a doubt, like what if my instruction is a jump instruction?
Okay,
Then
yeah, so we'll come to branch
instruction
instruction. Yeah, it's a good thing. We'll come to branch instruction. So we'll be spending at least 4 to 5 classes just working on branch instructions. But forgetting about branch instructions, is this somewhat clear? We'll again write it and see. So we'll, yeah, somebody remember. Okay, R1, R2, R3. So we have add R1, comma 2, comma R3. Subtract R4, comma R5, comma R6 again, and okay, so this was something else, right? So what was R4?
Subtract R4, R1, R5.
Okay, and this is R6, R7, and R8. Okay, so now let's write down the pipeline beautifully. So this is instruction 1. I do instruction fetch, instruction decode. Horrible. I cannot fetch this because that register is being occupied somebody else. So I do install. So this is first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10. So in 10 clock cycles, I am able to finish. So 15 clock cycles for unpipelined, right? If there was no stall, we were able to finish it very early. Right? If there were no stalls, I was able to finish it in 7 cycles. Because there was a stall, now I am taking 10 clock cycles. So what is your understanding from this? What is bad? What is the bad guy here?
stall.
Yeah, stall is a bad person, right? Because of the stall, instead of finishing it in 7 cycles, I am taking 10 cycles to finish all these 3 instructions. Okay. Now I can do something intelligent in this. Okay, dear, I hope, yeah, if you haven't understood, please ask me. So this is a stall here, right? So I just want to make sure that you understand the stall. So I want to reduce the amount of stall that happens. I have understood something. Can I do something here such that I can reduce the stalls here?
Swap the instruction 2 and 3.
Okay, so one guy is saying I can swap the instruction 2 and 3. Excellent. So I can swap the instruction. I can swap this instruction 2 and 3. But let's say I don't know anything about swapping. I can't swap. Let's say I have been dictated not to swap the instruction. Can I do something in the pipeline? You can do something. You can see something has happened, which you can use that information. So whoever answers this will get a prize this week. Think about it. I am sure you'll get the answer if you think about it. I can reduce. Okay, I'll give you a hint. I can
Sir,
reduce.
can we reduce the number of stages?
No. Let's say it's 5 stages. No, but think about this. This I can reduce. I can reduce these 3 stalls to some few more number of stalls. How can I do this? What do you know about the pipeline registers and what can I do about it?
Sir, after execution, we will have the result of
Yes,
R1.
since you already got a prize, you will not get a prize, but the answer is right. What Aditya is saying is that at the end of execution here in this register, what is the value that it is storing? It is storing the value of R2 plus R3. Does everybody agree to this? at the end of this, I have R2 plus R3. So this register has the value of what I want to put here, right? This register has the value R2 plus R3, because what is this instruction? This instruction is nothing. What is the user wanting to do? What is the programmer wanting to do? He actually wants to write R4, R2 plus R3. So this is what the register is, programmer is intending, right? It is just that he is using a register to store the value of R2 plus R3. But the programmer wants something like this. So I already have this value here. So where can I pass this value?
To write back.
No, not to write back. I
To
can pass it to the next.
execute of I2.
Yeah, I can pass it to the instruction decode register fetch of this, right? Because then I will be fetching the right value. Do you agree? See, what am I fetching? I am fetching the value of R1. Why did I not fetch R1 here? Because I have to wait for the R1 contents to be updated here. But if I'm able to pass this to this particular unit, I will be fetching what it has to fetch. Do you agree?
But sir, then we have to change the instruction, right? Like it will, by this register fetch, it will try to go and fetch R1.
Yeah, let's say, okay, let's say there is some mechanism. Let's say by some mechanism, this guy knows that at the end of this particular unit, I will know what I have to fetch. I have to fetch. See, what is this fetch doing? It has to fetch R1, right? So that there is no doubt, right? It has to fetch R1, R5. And why did it not fetch?
Because R1 does not have the value.
Because R1 value is not updated, yes, right? Value is not updated. Okay. But if somebody comes and tells you, you don't have to go to the register file to fetch R1, but I will give you that information. Will you still go into the register file and you will still be adamant to go to the register file and fetch something? If suppose you want to buy onions, will you always go to Big Bazaar? No, right? You might go to somebody who is giving you that. If somebody comes and gives the onions to your home, will you still go and buy that in the Big Bazaar? No, right? Because you are sorry. Will Shritesh go and buy Isaac Asimov again, the same book that he won as a prize? No, because he already has that, right? If somebody comes and tells this guy, that I will give you the updated value of what you are trying to look, then he will not go and register fetch it, right? So he will just fetch whatever is given to it. So I can actually move this here. Do you agree? Okay, we'll write it down, and if it's not clear, I will come back again. Yeah, go ahead. So I had instruction 1. So this was instruction fetch, instruction decode, register fetch, execute, memory, write back. At the end of this stage, I had R1 plus R2. Right. So that I hope everybody agrees, right? So this at the end of this stage, I had R1 plus R2. Okay. Then I have instruction fetch of instruction 2. Right. Then I cannot do instruction decode register fetch here because I have to get the value of R1. But at some point here, I forward this instruction. So I can do an instruction decode register fetch here. So this is stall. And then I do an execute memory. And then I write back. How many of you think that this is a wrong thing to do or it will not work? Actually, forwarding doesn't even work this way. There is a bit more subtle than this, but if you understand this, I think I can explain that in further classes. So this mechanism is called pipeline forwarding. All processors implement this because this is the only way that they can solve this problem. So I can implement pipeline. What does pipeline forwarding do? It will figure out that I have the updated value in some of the pipeline register, and the pipeline register will forward that value to whoever is dependent on it. So here, this guy is dependent, so it will just forward it. Okay, let's take a poll. Like you're not understanding, we'll come back to it again. Yeah, just answer the poll if you are not understood. We'll try to answer it. Okay, this time everybody's saying yes because they think I'm angry or something. Okay, I hope the answer was true. Yeah, but if you didn't understand anyway, please attend the tutorial. I'll try to have a tutorial for this because I want you to understand this before you finish this course. Okay, we are doing pipeline forwarding here. So there's a stall here. So instruction 3 will do, since there's a stall here, I cannot have an instruction fetch. So that you should keep it in mind because this particular guy is busy. So I have to have a stall here, and then there will be an instruction fetch, then there will be an instruction decode, register fetch, execute, memory, and write back. So in how many cycles did I finish? 1, 2, 3, 4, 5, 6, 7, 8. So I reduced the stall by 2 cycles. So instead of it taking 10 cycles, I am finished it in 8 cycles. So I implemented a hardware mechanism or hardware scheme where I did some kind of forwarding, and that forwarding helped me to finish this earlier. Of course, the forwarding actually doesn't work this way. Just to a caveat for you to know, this will forward it to this execution unit and not to this register fetch unit. Can anybody tell me why? So in hardware, actually, this doesn't happen. It will forward it to here. Why? Because this unit doesn't need that. This unit is just decoding and register fetching, right? So the where that value of R1 R2 plus R3 is needed is in this execution unit. So it is just passing on this information here. If you want to look at it the other way around, you can see it this way. So you have the instruction fetch unit, instruction decode unit, execute unit, memory unit, and write back unit. So what happens is, so there is this instruction fetch, and this is connected to this, right? And this is connected to this, and this is connected to this, and this is connected to this. But there is also one more connection that is going on, something like this. So I just forward it to myself so that I can continue the execution. So I can forward this particular guy to this here because that will continue the execution. So this mechanism, okay, if you didn't understand this, it is okay. Okay, let's come back to this later. We will draw the hardware later, but the idea is very simple. It's called pipeline forwarding. Okay, I will ask, since you guys are very now confident about.
Sir, sir, if like this seems to be something like if this IDRF instruction like step is not requiring that result from the execution of the I1, so then that stall process also can be removed and can be shifted one more step back.
This one, yes, excellent. Yeah. So you will actually get the prize because this is a beautiful answer. So what Amit, I was planning to ask this question later, but what Amit is saying is, I will do an instruction decode register fetch here. I will do an instruction. Okay, let's write down Amit's idea, right? And let's figure out whether it is wrong or right. Okay. See, that's why I'm saying everybody is a computer architect. It doesn't need any special skill. You just keep thinking. You will come up with the same. Like if given enough time, I am sure you all guys will come up with the same I1 like Intel design or ARM design or whatever, right? So that's the beautiful part of working in architecture. So what Amit is saying is, I will do an instruction fetch. I will do an instruction decode register fetch. I know that I have got a wrong value, but I'm still okay because the execution unit here will not get the value from here, but it will get the forwarded value from here. And then I have memory, and then I have write back. Then there is this instruction fetch, instruction execute, memory, and write back. So how many cycles did I take? 7 cycles. Is everybody okay with the answer? What I mean, or is everybody okay with Amit's idea, or does anybody want to challenge him? If somebody challenges him, they will take.
Sir, I'm just confused. Like there are 2 registers, right? So how do we know which one to take the previous value. Like
Okay, so what Gitin is saying is that now the input to this guy, right? That's what you're asking, right? The input to this guy
yes,
is
sir.
it by itself or by this register? Now, which one should I take?
Yeah, like two registers. We are fetching two registers. So
Mhm.
for one of them, we should take from the previous instruction, and for one of them, we should take from the new instruction.
Yeah, so like what
How
I
do you
answered
figure that
to, yeah, like what I
Is
answered
it
to
like
them
the
is
log
like,
function or something like that? Like whatever he said earlier. That
yeah,
bit.
like whatever we saw, right? Like I know that the bit
Okay.
is set, so I will not pass on the information. I will get this information from here.
Okay.
That is one design. Yeah, but don't get stuck to that design because
Okay,
the design
okay.
is wrong.
Not stuck. I'm just saying.
Yeah, but that works, right?
Yes, sir. Works.
Yeah.
But
So does anybody want to challenge Amit? So if somebody challenges Amit, he will get the prize. He or she will get the prize. So do you think that there's no mistake in this design? I'm surprised about that.
So maybe we can say that like the execute step is taking the instruction, whatever the memory is there from the previous step, IDRF step. So something like that is coming. Like it will not take the memory, whatever stored in the memory of the execution step of the I1.
No, I don't see any problem there, right?
Like in the hardware link that you drew, that you are drawing all the consecutive steps to be linked to each other, right? So you are not drawing the link from one instruction to the other instruction. So that is where I'm confused a bit.
Sir, when we're doing the execution, we're changing the registers. No, sir, in the second instruction.
Okay. 1 second. Let's write down this and then I'll again come back to this question. Okay. Does everybody agree to this kind of design? Okay. This is again a stupid way of writing it. But does everybody see what is happening here? There are 5 hardware units and there are 4 registers and you are passing from one register to another register. Okay. Is this okay? Now for this idea
Yes,
to
sir.
work, yeah, now for this idea to work, there should be somewhere something like this, right?
Yes, sir.
Yeah, what if I tell you that there is something like this in the hardware? Then will this work? So here what did I fetch? I fetched the, so let's think about I2, right? So I2 was fetched here. Let's concentrate only on I2. So now I2 was fetched. It was decoded here, right? And I fetched what? I fetched value of R1, comma, R1, comma,
So are you
R5.
able to do both? Like in one instruction, take something from the IDRF register and from the self register of execute?
Yeah, right. So that I can do in the same clock cycle. So it's just that the connections are different. So there are 2 duplicate connections here, right? If there was only one connection, I could have done only one.
Okay,
There are
okay.
2 connections.
Yeah, then it's fine.
Yeah. So I have fetched R1, R5. So I have fetched R1, R5. But this R1 that I have fetched is wrong. Why is it wrong? Because I should be fetching the value of R1 plus whatever this instruction 1 produced, whatever this instruction produced. But I am fetching some junk value because that has not yet completed execution. So now I have fetched R1, R5 and passing on to this execution unit. So this execution unit figures out that whatever I got as R1 is wrong and it will use its own value. Then it should work, right? So is there any other problem in this design? Okay, before I close the class, I have one thing that to note now. We'll again come back to it and again I'll bug you around this, guys, around this. So you'll be seeing a lot more of me in the future classes. So why a stall? So who created this stall? Why a stall? Because the way the program is written. Yeah, because the way the program is written, right? Because of the program. Right? The stall is because of the program. So this is the program that somebody gave it to this guy, so to this execution unit or to this pipeline. So these 3 instructions were given to this particular hardware, that processor, and there was a stall. But will the actual stall be visible to the pipeline or not is dependent on how you implement. If somebody had not implemented pipeline forwarding, they would have lost out. But since somebody has implemented the pipeline forwarding, it actually did not affect it, right? So there was no actual stall because I have implemented pipelines. So do you think that I can always get away with stall by looking at this? Can I always get away with stall? Can you give me an example where whatever I do, I will always get a stall? So this also gets a price. So there are 2 prizes this week. So you should give me a set of instructions where whatever I do, I will always get a stall. Okay, I think I am running out of time. Okay, forget that question. Did you understand till here? If you are not understood, we'll again come back to it. But are there any questions regarding this? Do you think this Amit's idea will work?
Sir, here one doubt, like, let's say if the first instruction and the third instruction are dependent, then while doing the second instruction, the execute, like in the register execute, that value will be overwritten, right? And then in the third step, we haven't written right back. So
no, what will,
will it work?
See, if I2 and I1 are not dependent.
I'm saying I1 and I3 is dependent.
But I2, I1 are not dependent, right?
Not dependent.
Yeah, so then there is no problem. This will get the value from here only, not here, right? So this will
But
get a value.
like I1 and I3 are dependent. So like I1
this
hasn't. Yeah, that execute. Where will it get the value from?
Yeah, you should tell me where will it get the value?
Because I1 hasn't completed right back.
Yeah, so
like,
do you implement pipeline forwarding for it or not?
Can we do that? That's my question.
Yeah, you should tell me. Can you do that? No.
Okay, I'll think about it.
No. You know the answer. Just think about it.
Yeah.
I can do it, right? I can do pipeline forwarding for even I3, right? So instead of this passing it here, I am passing here.
But that value will be overwritten, right? I mean, in I2, the fourth column, execute will again overwrite that value, right?
No,
I mean, the value in that register will again change.
No.
So in the second instruction, it's again doing something. It's not a dependent instruction. So in the value in that register will change.
Yes, right.
Then in fifth one, we don't have that value.
So what I can do, okay, I can still do forwarding. From where can I forward?
That is my question. Like we have to create a stall there, and then after that we have to forward from like a right back of the first one, something like that. We have to do.
Excuse me, sir. The next class is started.
Oh, sorry. Okay.
Oh.
Yeah. Okay, we'll meet again. Yeah.